Okay, we'll start the class in 5 minutes. Just waiting for people to join. Yeah, so it's just me right now. I'm waiting for people to join. Okay, we'll start the class. Let's see how many people join during the day, during the session. So, yeah, I welcome you all to another doubt clearing or problem solving session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor NP Padhy and Professor Premlata Jena from IIT Roorkee. I am Swastik Sharma. I'm a PMRF scholar at IIT Kanpur and I'm a TF. I'm one of the TF for this course, right? So the lectures are being uploaded on the YouTube regularly. I mean, I do it fairly very quickly, so I hope people go through them because whatever we will be doing now from this week onwards will require all the basics that we have covered from the previous few weeks, right? You'll see it from today's lecture only that after I finish relays, we start talking about these batteries and other renewable energy sources again. So yeah, so uh, I would request you to please watch the lectures, previous lectures, and that will help you in better, have a better understanding of what we do during the regular class. And yeah, it's a bad time to take the class as well. I mean, it's India versus Australia semi-final is going on, right? Champions Trophy. So I guess people are watching that. Anyways, that's why we upload it on YouTube. So yeah, last week we were talking about how the smart grids they have changed the way that they have changed everything. We have now generation at the distribution side. This generation has contributed to bidirectional power flows, which was not earlier considered to be as part of a passive distribution network. So when I say passive, passive means that we were only a load consuming entity. Now we have become more and more active. That means we are now producing as well as consuming, right? So, due to this, what is happening right now is there are a lot of gaps to fill. Like for example, we talked about you know what's happening with the protection schemes as well, right? So they suffer from false stripping. They are blinded by the kind of the blinded by the protection scheme used. Then the magnitude and the dynamics of the level of fault current also contributes to this peculiarity with respect to what is called as this smart grid protection schemes, right? So today, so last when we were finishing, I told you how it is beneficial for us to gauge the magnitude as well as the direction of the current, because not only because that will only help us to adapt these already present protection equipments or relays to the newer smarter grids, right? So we'll start with the discussion. I'll just share my screen. Give me a second. Okay. So There's no way I can, yeah, I mean, it's fine. Hmm. So, so we were discussing, right? Why do we require protection at all? I mean, because, we need to protect our devices, mm, we need to protect our equipments that are being used to transmit power to the distribution network as well, right? But why do we require adaptive protection? It's because of the all those things that we discussed last week, right? What were they? So we want to protect ourselves from false tripping. We want to protect ourselves from the magnitude and the level of the dynamics in the level of fault current. And we need to figure out the direction, because there is bidirectional power flow at the distribution side now. We need to figure out what is the direction of the fault current, so that we can trip the associated relay and not discontinue or disconnect the feeder at all, right? So the main thing, I'll write it in red, is direction, right? And while we were studying, I told you that directional overcurrent relays form of relays are being used for this protection schemes, for adaptive protection schemes at distribution side, right? So we discussed all of this, and now we will talk about what are the ways in which we are using them or utilizing them, right? So let's consider this arrangement in which we have this source, and then we have two bus scheme. Let's assume there is a two bus scheme or three bus, right? And then we have loads at both the end, and then we have, just a second. So I told you last week as well that we need redundancy when we talk about protection, right? To increase the reliability, we need redundancy. And when I say redundancy, it's like that there should be a backup, to onto which you can count on, so that you can know that your system is fairly protected, right? So let's say there are these two relays. Now let's assume that a fault now takes place, and a fault takes place just ahead of this, right? Relay 2. Now when the flow of power is like this, when the flow of power is this, so when the flow of power is this, so what do I want? I want my relay 2 to trip first, right? I don't want my relay 1 to trip, because the load connected at this bus 2, let's assume this is bus 1 and bus 2, this can still be powered if um, I have not switched off relay 1, right? I want to disconnect my further buses that are connected to bus 2, not to bus 1, right? So what happens for fault F? R1 becomes the backup relay and R2 becomes the primary relay. Right, so what I want is, for this fault F, I want my relay 1 to trip first. And if the operation is still not achieved, I mean, if this fault is still not recovered, if the condition is not averted, I want my relay 1 to trip. So that is how the redundancy is ensured in the system, right? By having backup relays. Now, how do I know? Okay, let's assume that relay 2 has not tripped. How can I assure that now relay 1 should trip? So there should be a minimum time, right? It should sense this fault for a particular amount of time before having operated that relay, having to issue that trip signal from the backup relay, right? So this minimum time is called coordination time interval, CTI, right? So this is nothing but this talks about what is the minimum time gap between the operational minimum time gap between both of the relays before they are made operational, right? And this is generally taken in for generally it's between 0.3 to 0.5 seconds. See how quick it's that. So I want my relay, backup relay, to act uh, only if the total operational time between the relay tripping of the relay 1 is 0.3 to 0.5 second, right? And this CTI is used to uh, coordinate both of the relays so that they work together in dissociating a fault if at all relay 1 fails. Right. But now let's say that, so I told you earlier, right? So now the DRs are into the scheme, and now there can be times in which the level of fault current, it can change. It can change. For let's say relay 1, it can be a different fault current that it can experience, and for relay 2, the fault current it experiences different. So there is one setting in all of the relays. It's called plug multiplier setting. Plug setting multiplier, sorry. PSM. So what does it say? So the idea of PSM is to check on act only when the current or the fault current reaches to a particular threshold. So it tells you to act only when the current has reached to a particular threshold. So that means it's fault current upon pickup current. So where pickup current is nothing but current threshold that tells the relay when to act. Right. So so the pickup, so having this multiplier, I can tweak it in such a way that given a fault current, let's say my PSM is 1.2, right? So 1.2 of my I pickup, so then it acts only for a fault current of 1.2 times the pickup current. So so this is how you ensure that the magnitude is not, some. So how do you ensure this magnitude? So how does this PSM come into play? So I told you earlier, right? So you have current transformer CTPTs to measure the voltage and current for the relay. Relay can only take 1 ampere and 5 ampere currents, right? So what you do is, based on the turn ratio of the CT, you can change the plug setting multipliers. You can change the PSM in such a way that it can pick up fault only for that amount of current that it is designed to. Like for example, if my plug setting multiplier is 1.2, it you have to change the turn ratio of the CT in such a way that it picks fault current only for 1.2 times the original pickup current it was designed for, right? So this is a very interesting setting in the relay. It's used because DRs, they are changing. You can have different DRs and they can contribute differently to a fault current, and you have to have, it cannot be like for a particular relay, when a manufacturer makes a relay, it makes only for a 5 ampere fault current, let's assume, and it's just a number I'm talking about. 5 ampere is very less, but let's assume, right? But now what you're experiencing is a 4 ampere fault, and you now have to get a new relay. That should not be the case, right? Why will you get a new relay when you already have a relay? So this PSM ensures that, the setting ensures that the already present relay in your that is given by a manufacturer can be used for any kind of fault current that comes from your um that is being taken from your DR, or any fault, for example, right? There is one more issue. Like for example, I recently told, right, in the previous class as well, that there is something called as inverse definite minimum time, IDMT, characteristic of an overcurrent relay. So what is inverse definite minimum time? It tells that the time and fault current it experiences to, sorry So it says that the level of fault current, if the level of fault current increases, the time taken to issue a trip signal by a relay decreases. So as the magnitude of fault current increases, your time taken to issue a trip signal also decreases. So in a way, that what you want is, you want to make sure that you have some kind of setting, so that you can manipulate this inverse relation as well, right? For example, you can't simply use an overcurrent relay anymore, right? I told you, you have to have a sense of directionality as well. In last class we discussed. And so for that, what you require is, you have this time dial setting, or a time setting multiplier, or a time setting multiplier, TDS or TMS. So what is the use of this? The use of this is to guarantee, or give you, um, an adjustment setting, so that you can adjust the speed in which your relay trips, issues a trip command, right? So it adjusts the speed which a relay issues a trip signal, right? So these are a few characteristics, or settings that you have for a relay, that gives you an edge, right? You want to make your protection equipments adaptive for your for any purpose that you are using for. And you have to have this adaptive protection, because of the dynamics that are now coming into play due to the proliferation, or increasing usage of DRs at the distribution side, right? So so for this, what we have is, for smart grids, at least for smart grids, researchers have proposed new relay, which is called a directional overcurrent relay. Also called as DOCRs. So these relays, what they do, they use all of these settings, and they have the manufacturer specified setting as well, to give you adaptive protection for the kind of usage that you want to devise from the relay, right? So let's talk about this DOCR. I told you I will discuss in the this week, so I have to discuss this before moving on. So let's talk about directional overcurrent relay. So as the name suggests, there are working principle surrounding is that it has an operational so sorry it has two operational conditions. That is, it can measure the overcurrent as well as the direction of the fault, right? So the overcurrent condition is nothing but, so any overcurrent relay, what it does is, it checks that if the fault current exceeds the pickup current of a relay for a particular amount of for a threshold of time, it issues a trip command, right? So fault current is greater than, the second one is the directional condition. So we discussed last week why it's important, for this for the direction condition. It's because you want to make sure that the kind of fault current you're witnessing, so that you appropriately issue a trip signal to the relay, so that it does not, you know, uh, it does not disrupt the flow of current to different feeder sections of the feeders, right? And that's where the direction component comes into play, that you want to make sure that, because there are bidirectional power flow in smart networks now, smart distribution networks. So you want to make sure that you are able to sense, okay, if the fault is in front of you or behind you, so that you can uh, appropriately act as a sort of a primary relay or a a sort of act like a primary relay or a backup relay. Yes, Devansh, you've raised your hand. Okay. So you don't need to raise your hand. You can just simply, unmute yourself and talk. I mean, there's no issue with it. So there was a, yeah. So yeah, that's where the direction needs to, you need to be able to sense if the fault is happening before you or after you, and that's where this condition plays. So right, so how does it do? So first of all, you require a polarizing quantity or a reference, right? So with which you can sense, okay, especially for a directional element, you need a polarizing quantity, and for this we discussed last class that the directional element or the polarizing quantity is the voltage. So you take voltage as the reference, right? Voltage phasor, some V angle 0, right? So you take, let's call it, yeah, it's V angle 0, or we call it VP, so it's polarizing voltage, right? So you take this reference into play and you measure the relative or the phase angle difference between the polarizing quantity and your fault current, so that you are able to sense, okay, where is the fault occurring? Is it forward to you or backward to you? And how do you do that? It's by sensing, it's by deriving this torque condition. So your relays, they what they do is they measure, or they quantify the torque associated with, you know some internal disk rotation or something like that, so that they sense this torque, and based on the magnitude or the direction of this torque, they sense, okay, if the fault is occurring forward or backward. So if T, the torque quantity, is written as something like this: theta V minus theta I minus an alpha. So we'll talk about each component. So Vp is your polarizing voltage, If is your fault current, and this condition here, theta V and theta I, is your phase angle difference between voltage phasor and current, right? And alpha. So alpha is your relay characteristic angle. So what does that, why do you use this? It's because, it's generally used because the transmission network or the distribution network has an inherent impedance angle as well, right? So to make sure that the maximum torque angle that you can derive, or it's also called as MTA or MTA, it's the angle at which maximum torque occurs. So what you want to do is you want to make sure that the impedance of the transmission line or the distribution network is accounted, so that you can check, okay, at which angle the maximum, so that you can phase shift appropriately, so that you can have a correct sense of directionality of how the fault current or the fault current is behaving. Is it behaving in front of you or backwards of you? So this generally is between 30 to 60 degree, and it's 30 to 45 for transmission and 45 to 60 for distribution network. It's higher for the case of distribution network because of a high R by X ratio. And yeah, now let's talk about how does it sense. So what it basically does is it's measure the if T is greater than 0 or less than 0. When I say greater than 0 or less than 0, in the internal rotation of the this inside it there's a disk or some component which is rotating, and what it does is it checks if the rotation is in the positive direction or opposite direction, right? Based on that, it sends, okay, if T is less than 0, It means that it does not have to trip because the torque is behind of it. And if t is greater than 0, it says it has to issue a trip command because the torque is in front of it. Now you'll come and say, okay, there's this one thing that irks me the most is with respect to this torque condition is that I call alpha as the maximum torque angle, right? MTA. But if you see at alpha equal to theta v minus theta I, which is supposed to be the maximum torque angle, sine would become 0, right? So generally, there is an internal phase shift inside of the relay that is specified by the manufacturer. Whenever you get a relay, there is this internal phase shift that it specifies if it is in plus 90 degree or minus 90 degree, where it tells you, okay, the 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 voltage and current phasors can be dissociated or phase shifted with respect to whatever they are experiencing, but the relay internally, as an internal operation, phase shifts and the angle by 90 degrees, so that at maximum torque angle, if theta v minus theta I is equal to alpha, it is equal to 90 degrees. So that is present inside of it inherently, right? So based on this, based on how the torque is operating, it senses, okay, if this is reverse or in this forward of it. Now this whole thing is it's for a relay which is supposed to have a rotational element, right? A disc or some form of a component which can rotate, and these are only present in mechanical relays. Right now we are using digital processing microprocessor based relays as well, right? For that, I mean, this was not talked about by ma'am, but still. So so for microprocessor based relays, so what microprocessor does is it is good in computation, right? So it computes what is called as the sine of the real value of dot product between fault current and polarizing voltage, which is the complex conjugate of this. By calculating this sign and by having if it is positive or negative, it can issue a trip command or a trip signal, right? So modernly, what they do is now they are resorting to this, what is it called? Sorry, yeah. So competition in which they are calculating this product, and they are finding out the sign, and based on that they are issuing a directional signal. So this gives a directional signal. Positive it is in front of it, and negative if it is behind. So this is how DOCRs operate. So now we have figured out, okay, like okay, we got everything right, but how do we use them in a real setting? How do we know what kind of plug setting multiplier should we use? How do we know what kind of time dial setting we use? So for that, the instructor has given this illustrative example which they have also used in their research. And just a second. Yeah. For this adaptive protection scheme, what they're using, what they're doing, essentially doing is they're using sequence currents, right? So what they do for sequence current is they know for faults what usually happens for faults is, so faults may cause system to go unbalanced, right? So due to this, what happens? Unbalanced operation, your sequence components arise, right? By using this condition, by exploiting this unbalanced condition, what they are doing is they are essentially exploiting how to utilize or come up with a plug setting multiplier or a time dial setting or a time multiplier setting, right? Okay, so so what were yeah, so keep in mind that this condition, if for let's say for a true system, they may not be applicable for a three phase to ground fault. For a three phase to ground fault, they may not be applicable because they are balanced in nature. So this kind of a fault is a balanced fault, and it is directly across three phases to ground fault, right? So this may not be applicable to this condition. So I just sorry. three phase to ground faults. So it's not app. Okay, so what do you do? So how do you come up with? So first of all, you calculate the plug setting multiplier by for the for the so PSM for the primary relay. What they do is they calculate the positive sequence current. So fault current associate the positive sequence fault current. This component is positive sequence fault current, and IPJ is the pickup current. So this essentially is your plug setting multiplier for your primary relay, and for your backup relay, what you use is you use the negative sequence current, which is I2C Fij. Okay, so P and B here denote primary and backup respectively. C is the operation node at which the distribution system operation node at which it is connected. 1 and 2 are positive and negative sequence respectively. Fij is that for a fault at I and a relay connected at J, what is the fault current it is experiencing, and J is the node at which sorry, the relay, it's talking about the relay J, right? So based on this, what they do is they calculate a new operating time, which is for a backup relay and primary relay using this plug multiplier setting. They come up with this operation time for each of these primary and backup relay. And what they do is to calculate a new time multiplier setting, they just use this method to come up uh, with a new time multiplier setting compared to the old one by just comparing what the positive sequence and negative sequence currents are, right? So what they do is they now have two things. So they have now adapted their um, PSM and TDS or TSM, right? TMS. Now what they need is they need to understand, okay, what is the direction of the current. Now they found out they adapted the time dial setting and plug setting multiplier, but what is the direction? How do they adapt it to the direction or to sense the direction of the fault, right? So for this, what they do is they use the concept of superimposed currents. So how do they come up with that is they assume this system. This is a 3-bus system in which at G your relay is connected, right? Now for a pre-fault system, which is this is a pre-fault condition. What they do is they calculate this I1 pre, this thing. Just a second. They calculate this thing, right? So how do they do it? They simply just use mesh analysis or KVL, right? So I'll do it only for one. For the rest of them, you can do it on your own at your own convenience, right? So V, what it will be? It will be IE0 Z1E minus. So let's club them because they are the same. So let's call it, oh, it's Z1U, sorry. So for this IE0 mesh current, this equation comes. Similarly, you do for IH0. Let's assume this. So you have everything VH plus IH0 and it's how much? Oh, sorry, it's Z1U IH0 minus IE0. Right. Using these two conditions, you can come up with, a value of IH0, and you'll see that your pre-fault current is nothing but I1 pre is nothing but your IH0. So you have two equations and you can come up with IH0. So I'll just give you a final formula. derive it on your own because it will take me time if I do everything. So the final formula would look something like this. If I write this side as P, this side as Q, so Z1P is nothing but Z1E plus Z1EG, and Z1Q is Z1G plus Z1, sorry, Z1H, right? And now I have Z1PQ, which is the parallel combination of both, and this parallel combination is nothing but Z1P plus Z1U and Z1Q plus Z1U minus Z1U square. And I'll just take this next. Hmm. So your the final form would look something like this. Let me just check. Hmm. So your I1, so your I at 0 would be Z1U upon Z1PQ VE minus Z1P plus Z1U upon Z1PQ VH, right? In terms of V and VH, it would be something like this. So this is your pre-fault current. So what you have to do is for the before fault, how was your pre-fault current looking like? So this is what you have calculated. Now similar analysis you have to do with for this fault at condition 1, sorry, fault at F1 and fault at F2. So this one here is fault at F1, and if you can see your IF1 is nothing but it's still IH here, right? Which is IH, right? So this one be IH. So you just have to figure out this IH current and you'll be able to tell, okay, what is your post-fault current for fault condition at F1. Similarly for F2, what is your fault current? Okay, so similarly for F2, your fault current, it is nothing but IG dash. So for fault at F2, you have to calculate or do the similar KVL for for these two nodes and find out this IG dash current. Now you found both of these current, right? So what is the plan? What is the plan? What are you going to do? So what we are essentially looking for is we want to superimpose both of these conditions, right? I1 F1 minus I1 pre and check what is the fault looking like. So what you do is you check delta IF1, and what you do is you so post fault and pre fault, you subtract both these are phasor quantities. So what we are finding out essentially is a phasor quantity. So you have to do it, in terms of uh, this rectangle, yeah, these with phase angle, right? So you have to do it with it's called polar coordinates, right? So you have to do it with respect to this. Similarly, this will also be in terms of polar coordinate, nothing but I1 F2 minus I1 pre. So what you're doing is you're superimposing your pre-fault condition to your post-fault condition, and you are then checking out how your magnitude and your phase angle is looking like. So most importantly, what is the phase angle, right? So how do you check is you get this phi f1 by subtracting the angle from your I1 f1, the superimposed current from your pre-fault conditions, right? So once you do that, what you want to check is how, in order to check it, it's through this lookup table. So given the flow of power, if it is upstream or downstream, your the phase angle would be different, and for different fault conditions, right? Let's assume for this G, your relay is connected at G, and what you want to check is that if, let's say, your flow of power is downstream. So when I say downstream, it's this from grid to DR. So for this, this relay from experience, because you are looking at it, that F2 is in front of it, so F2 is a forward fault and F1 is backward fault, right? But how does this, right? But how does this translate to this value that mathematically? Because relays can only do mathematical calculation, right? You can't tell them, okay, fault has occurred over here or there. It has to do it mathematically, right? So what you do is you check this phi f1 value. So based on this phi f1 value, what you do is you check if it is leading or lagging, right? If it is leading, that means it's positive, and if it's positive, that means the fault point is um, yeah, uh, it's in reverse direction, right? So if you see, let's say that just a second, let me, yeah. So what you do is you see your pre-fault. I'll do this. So you see your pre-fault current phasor, and you see your delta IF1 F1, right? So you see it's leading by phi F1, right? So that means that the value of this is positive, right? So if it is positive, what you have to check is how the fault is looking, right? So since it's positive, phi f1 is positive for this condition, and I told you positive denotes forward fault, right? And as you can see here, since this is positive for a downstream condition, for a positive phi f1, your fault is considered to be a forward fault. Now for this condition, when the power is flowing downstream, I know, sorry, F2 is your forward fault, F1 is your negative fault. Why is it positive? This is downstream, right? Just a second. Let me check. Yeah. Some, I think this lookup table is wrong. Hmm. So it's loading. Just give me a second. Hmm. So I told you if 5-1 is positive, right? If it's lagging, it's downside, right? And it should be negative. It's something is wrong. Let me check. So in this paper, they have, oh, sorry. In this paper, they have talked about, if you can see it on my screens, I feel you are seeing it on my screen, right? No, you're not seeing. Just a second. Let me share my screen. It can't work. I have already one. As a result, the phi f1 is found to be positive and plus 1, which is a reverse fault, right? Yeah, this is wrong. Plus 1 is considered as a reverse fault, and hmm, hmm. So this is downstream, and phi f1 is positive, so it's forward fault. It is negative. So as far as I know, and I've checked, plus 1 is generally considered for a reverse fault, and minus 1 for a forward fault, right? So this I need to check if this is correct. Anyways, so yeah, if the phi f1 is positive, since it's leading, right? It's positive. So I know that it is to be given a plus 1. That means it's a reverse fault, right? And as you can see that for G, it is given a plus 1 signal, and the fault is behind it or backwards, right? Similarly, is phi F2 is negative for this downstream condition only. It's negative. I issue a -1 decision, which means the fault is in front of it, and as you can see, the fault is in front of it, right? So why do we correlate positive to +1 and it to reverse? It's because the fault will lead only when it is behind of it, right? And that is what is being talked about in this and in this paper as well. I don't know why this is given over here. Anyways, so let's talk about the relay when it experiences an upstream current. That means the DR is now powering or energizing this transmission line, right? So then F2 becomes forward, sorry, F2 becomes backwards and F1 becomes forward, right? So here you can see that my pre-fault current is here and my F1 lags, right? Since F1 is lagging, that means phi F1 is negative, right? And phi F2 is positive since it's leading. You see, it's leading. So in anti-clockwise we lead and oh sorry, my bad. Yeah, yeah, +1 -1. Sorry, just a second. So we have deplete. Sorry. Okay. Hmm. So here pre-fault condition is this, right? I was going clockwise because of this direction of this thing, right? Anyways, my bad. So your phi F1, since it's lagging, it's negative because in your three-phase circuit as well, it's something like this, right? A lags B by 120 degree and A leads C by 120 degree, right? So my bad, I assumed the direction wrong. So right, phi F1 is lagging, so that means the angle is negative, and if it is negative, the fault will be in the reverse direction for the downstream current, right? And that is what it tells you, okay? It's backwards. And similarly, phi F2 is positive, that means it's leading, and if it leads, you sense that it is forward, right? You can do the same analysis for your upstream condition, and based on that you can check, okay, if what kind of decision your fault current is making, okay. Yeah, my bad, I was assuming this direction of current. I should have, not taken this as I should have just taken I1 pre. Yeah, I'm sorry, my bad. Yeah, so this is how you measure the with respect to how it is lagging or leading. You measure if the direction of the fault current is in front of the relay or in the backwards of the relay, right? So yeah, just a second. Hmm. Okay, so where was I? Yes. Hmm. With respect to I1 pre, we are finding out. Just a second. I'll come back to this. I'm a bit flustered right now to take my time. Yeah, similarly for this superimposed adaptive sequence current-based production in what, so now what you have done is you've got the direction sensor as well. I'll come back to this at the end of the section. I just need to, get my head right. I mean, I'm not thinking it clearly. So anyways, so you go, if you let's say got the direction right and now you have the direction, so what you need to do is you need to sense, okay, the fault current contributed from the synchronous base DR, it is different from what is sensed by the inverter, right? I have already told you. the fault current coming from inverter based DER is limited to twice its rated current, and similarly fault current coming from the synchronous based DER is rated 5 times its rated current, right? So now you see the both of them contribute differently for a for the same fault current, right? Now even though you've got your plug setting multiplier and everything, but how do you make sure that when it is sensing its direction, the magnitude or the, you know, how you're taking the the phasor the phasor contribution, the relay, it's seeing, okay, the phasor contribution, sorry, vector contribution, vector addition from both of these relays, the contribution from the both of relays are somewhat similar, right? But since SBDR contributes more than your inverter based DR, you need to make sure that whatever the contribution is, it's similar, right? So what you do is, for an IBDR, your fault current, the delta IF, when you calculate, you add your pre-fault current magnitude to it. Why do we do that? It is to increase its contribution because it is less. It is only 2 times the rated current. And in the case of SBDR, you subtract it so that you decrease its contribution, so that both of them come on to the same footing, right? And rest of them, what you do is you go ahead and you calculate delta IF1 and everything, the same thing that we did earlier as well. Your characteristics are how you're calculating, your time dial setting, everything remains same. Only the contribution, to map the contribution from a synchronous based DR and inverter based DR, you just do this technique, right? And by this, what you do is you can have a holistic approach to, you know, adaptive protection for both for the smart grid, right? So this is in their paper, so I will suggest, if you want to read more about it, they have given the link of their paper by Premlata Jena ma'am, and you can check if you have, right? Just let me think here. If my delta IF1 I'm taking with respect to pre, and based on that I'm calculating the previous, and here the direction is different. Okay, so what you're doing is you're essentially calculating IE1 F1 and I1 pre, right? And you're superimposing so that you calculate the phase angle phi F1, right? Okay, got it. Okay, let's assume that your fault current at 60 degrees, your fault current phase angle is 60 degrees, and your pre-fault condition, it was 30 degrees, right? Then it comes out to be 30 degrees, and since it's positive, that means it's leading, right? So 60 degree and minus of 30 degrees with the minus 30 degree leading, right? Yeah. So what you're doing is you are essentially calculating, okay, for example, if it is, sorry, if it's positive, right? So it's one angle. So it's lagging, right? So what you do is, if it's positive, it lags, right? And if it is lagging, what you do is you say, okay, it's lagging. That means the fault is in front of you. Okay. So I was correct the first time. I was correct the first time. Delta phi f1, if magnitude is positive, so this should be delta here, delta here. It's leading, right? It's just a second. Just let me open So if it is greater than 0, it's leading, right? It's leading pre-fault current. It's lagging, right? The instructor's sheet. Hmm. So it's negative here, right? Okay, I got it. So let's, yeah, it took time, but yeah. So, so with respect to I1 pre, if you see this delta IF1, this phi F1 will be negative since it's in anti-clockwise direction. So if it is negative, what does it mean? It means that it lags, right? If it lags, that means the fault is in reverse direction, right? Similarly, for the same case, phi F2, this, since it's positive because it's in same and clockwise direction, that means it leads. So since it lead, it means fault is in positive direction. So what you do based on the based on this yeah, based on this lead or lag, you find out, okay, how the what is the sign of my phase angle difference, and based on that you figure out a +1 or a -1 signal, which tells you, okay, if the +1, it is in forward direction, -1 if in reverse, right? So you do this and you see that for both of them it comes out to be like this, and for this, if you see, F2 is in forward and F1 is in backward. Same analysis you can do with the downstream current, right? Yeah, I got a bit confused, but yes, that is how you do it. I mean, I was just, this direction irked me. Okay, so you take Ivan Pre as your reference, right? That is what superimposition is. Yeah, my bad. Sorry. Yeah, so this is all what you need to see from how to make your already present protection schemes adaptive uh, for your DER based distribution systems now, right? Next, the instructors moved on to, the storage systems, because now we are moving on to, development of microgrid. So we understood everything, how microgrid, what are the components that can empower a microgrid. Then we talked about the monitoring systems for our microgrid. Then we talked about what is the protection systems involved in microgrid. Now let's talk about the whole concept one last time, so that we're all on the same page. It's just a recap of what we did in the week 1 and week 2 or week 3 lectures, and then we'll move on uh, to officially declare what a microgrid is, how a DC microgrid comes into play, how an AC microgrid comes into play, right? So for any DG rich or renewable rich system or a microgrid system, one thing you'll find for sure is the storage. A storage is a very important part of your microgrid. It's because it does a lot of things in which your regular fossil-based fuels are inefficient, right? First, it can charge and discharge both, right? So when it charges, it acts as a load, and when it discharges, it acts as a source, right? So you can have both the qualities of a source and a load in the same uh, in the same unit, right? So this gives us a better advantage in, what we can have a better, we can form our renewable energy resources in a way that it is able to give a continuous output. Let's say, for example, your solar was forecasted to give, something like this. But due to cloud cover, it gave something like this. You forecasted properly, but yet there was a cloud cover which you couldn't predict, and now the output has diminished, but you promised this extra thing, right? So how do you make sure that you are able to provide? You can couple it with a battery in such a way that it is able to give you this extra power, so that if you have committed that extra power, you are able to give, right? So this intermittency and variability of inherent variability of these resources, it can be used to, uh, it can be used to to diminish them, right? Then it can be used to flatten the load profile, right? I I've talked this a lot of times. What we have right now at the residential side is a diurnal peak. We we see a we see a morning peak and then an evening peak, right? Now, for you, this peak won't be any issue, but from a systems operation perspective, this peak is very harmful. Harmful in a way that your DSO, if you know the power demand is more, it has to pay more price. The price of the power at the same time increases. Second, because of this peak, you need to ensure that you have enough ramping capability. This ramp down and ramp up capability you need to have, and in your present thermal based power plant, this ramp up capability is not there. So what you have right now is 3 to 5% per minute of ramping capability coming from thermal power plant, right? It is very less, and this peak can be huge. It can be more than 500 megawatts sometimes, right? So how do you ensure this? So for this, what you can do is you can have uh, a sort of battery which can discharge it. So let's say you want to have a flat load profile. That means you want to experience something like this, right? So a flat load profile in essence is not is not something that you can have. But let's say you want to have this flat load profile. What you can do is you can charge at peak, at low demand, and you can discharge at periods of high demand, right? Using this, what you can do is you can form or flatten the load curve so that it can be easily maintained by the system operators, right? Next, because you are specifically targeting the intermittency and variability of the renewable energy system, you can indirectly or directly reduce your reliance on these fossil fuels as well, right? Also, they can help you in grid stability. So because they're inverter based resources, so what you can do is you can use them to exploit PF control or QV control, right? So you can do that to have a better frequency support or voltage support for your distribution system, or anywhere where it is planted. And then you have it for a black start action as well, because they can immediately start powering your system. So thermal based power plants, they take at least 12 to 6 to 18 hours to fire up, right? There are a lot of things that go into place. You have boilers that need to come up to a certain temperature so that they can convert this water to steam. And you these auxiliary power units, you need to have these suction pumps, these vanes, ventilation, etc., to be working, right? And so you see, a thermal power plant needs power to be able to give out power, right? For that, let's say a blackout happened, and if a blackout happened, your power plant goes into is not producing anymore, and it stopped functioning. This batteries can be used to give a black start action. Right now, for black start, what you use is DGs, distribute this diesel generator sets, right? But if you have batteries, you can use them for this black start capability, and that is where the importance comes into play. But there are non-electrical storages as well. So we have discussed this not million, but many times in the first 2 weeks. So for mechanical, you have um, flywheels, you know, and you can have yeah, I forgot. For electrochemical, you have hydrogen systems. You can store hydrogen, and then you can use them at a specified pressure to be able to you know hydrogen systems. You can have accumulators as well, so you can use you know you can use them to store some form of a liquid or chemical compound at a very high temperature, so that you can use it at a later stage to rotate your turbine or something like that. It can act like a storage device, right? And then you have thermal storage as well, like your this the solar based water heaters, right? They are thermal storage. So what you're doing is you are using the thermal power to decrease the reliance on electricity, right? So all of this is a very important topic, and storages are coming up with a better uh, so that they are being deployed in a better in a better way at the distribution or smart grid side, right? Now there are some key features that they need to have before they can be used, uh, they can be made operational. One is that they should match the properties of the power system. When I say they should match properties of a power system, is that let's say that I have a specified voltage at which I want it to be, um, give power, and this voltage is dictated by the point of common coupling, right? PCC. So your battery should be able to match that voltage to be able to, it should be able to match the properties at which it is being able to use, is it is being used. Then you need to have a sufficient storage capacity, right? Let's say that you have a battery, but it can only store for, 20 minutes. So what is the use of that? So it should have a sufficient storage capacity. If it has no storage capacity, then it is nothing, right? You want it to have some storage capacity. It should have a minimum storage period. What I mean by it is that it should be able to provide power for a given time duration. Then there should be charging and discharging times, same time duration. There should be a required energy density. When I say energy density, it means that per unit volume, how much kWh energy it can store, right? And then location is also it also plays a big thing. So they require, if you want to go with a very huge system, they require a very large space. You can see online, I mean, they require a very large space. So that is one thing, and environmental factors comes into play. So mining of these lithium ions is not cheap, and it's not that easy, right? You have to excavate a large area to be able to mine them. So recently in J&K, this in Riasi district, I feel, in Jammu, they have found these huge resources of lithium ions, right? So what they're doing is they're now excavating that area to get lithium out of it. And then there should be minimum number of storage cycles. Let's say I give you a phone, and I say that it can only store for 20 charge or discharge cycles, right? So will you be able to use that phone? It's nothing, right? So you need some minimum number of storage cycles to guarantee the operation, right? So this is where it is used. Now, there are some key terminologies associated with this. I hope that you have went through the lecture, but still will cover. So the first thing is battery duty. So what I mean by battery duty is it's the sequence of loads to supply, right? So given that you have some load coming, so it should be able to supply it for the particular amount of duration that demand is there, right? If it's not there, it's the so battery duty tells you how much of power it can give out or discharge for a particular sequence of loads that it is experiencing, right? Then you have cell size. So a battery consists of individual cells. Each cell has a particular capacity, right? And the cell size tells you about the capacity of the cells. Third is your equalizing charge. So I've told you earlier, right? So what you have is that there can be at times for lead acid battery, we can say it definitely that the sulfuric acid that is present inside of it when it starts discharging, it creates the sulfuric acid. And what it does, this sulfuric acid may not be stored equivalently across the cells, right? And since it's not stored equivalently, what happens is the voltage at different cells the voltages is not same across all the cells, right? So what you can do is you can uh, make sure that all of the cells are balanced, they have equal charge. What you do is you operate or you correct the inequality by operating it at a voltage level which is greater than its nominal voltage level, right? And that is called equalizing of the charge, where you equalize the charge across all the cells. Fourth is your full float operation. So connected across all the loads across a DC bus, it's called as full float operation, right? Storage is DC in nature and it is only able to uh, with the help of converters, it can power AC loads as well, but in itself it is only able to empower DC loads, right? So full float operation tells you that the for a DC system, operation of a DC system connected with the battery. So there are other key terminologies as well. I will tell you about rated capacity. So rated capacity is the capacity of the battery. So the capacity of battery is generally measured in terms of ampere hour. When I say ampere hour and why not kilowatt hour, it's because ampere hours tells how much of current it can give out for a particular hour, right? So kilowatt hour is nothing but ampere hour times voltage divided by 1000. Now, for different voltage levels, the stored energy will be different. But the key terminology that comes with the specification of the battery is ampere hour only, because for a particular ampere hour, we know that, okay, 100 ampere hour is its maximum capacity and it can only store up to 100 ampere hour. Kilowatt hour is a derived term based on the voltage level it is being charged at, right? So the capacity is generally given in ampere hour. Right. And we discussed battery modeling as well. So how do we model a battery? I told you it's with respect to RC circuit. So we have RC equivalent circuit in which the number of RC, I would request you to go and watch week 4 lecture to be able to better understand the how batteries are modeled as RC circuit. But still, to give you a brief review, what you do is your battery is measured as an VOC, which is the open circuit voltage, connected across a self-discharge circuit resistor, which is then connected across RC circuits. So with each RC circuit, what you're doing is you are trying to measure the temporal dependency of the open circuit voltage with that of what internally is happening in the chemistry of the battery. So if you increase the number of RC circuit, you produce a better and a better version of your model. And uh, yeah, ma'am, by increasing the number of RC circuit. But if you increase the number of RC circuit, the complexity of modeling that circuit also increases. So you have to have, you know, some trade-off between complexity and a better model. So this model in which what it shows is that at discharging and charging, the resistances can be different. This resistance measures the voltage drop that it experiences when it discharges or when it charges. These diodes model the what do they model? They model the flow of current, if it is charging or if it is discharging. Let's say when it is discharging, Vc is greater than V, right? Then only I current will flow will flow from Vc to V. So when Vc to V, it is discharging, and since it's discharging, this would be positive, this would be negative, and what you're doing is you can have a load over here, some load, and it is discharging it to that load. Now let's say you are charging it, right? So to charge it, this V should be greater than Vc, right? Only then the current flow would be in opposite direction. So once it is in opposite direction, this diode will work, this would block it, and your expected voltage will be V minus IRC, right? So this is how you can use these equations to model the charging and discharging, where you use the capacity and the battery discharge current or charge current to model it in such a way that you are able to come up with an with the SOC model, right? Now, a battery has several things that affects its performance. One is temperature. At higher temperature, what it happens is the formation of cracks is more. So battery internally forms cracks, and when it forms cracks, the ability to store power, store energy decreases over the time period, right? Then you have higher DOD or SOC even. So if you have a high DOD, your battery's performance will vary, right? If your if it decreases at a higher rate, if the depth of discharge is more, the volume that it has to charge will also be more, and it indirectly increases the temperature of the battery as well. So what affects yeah, the voltage at which it charges. If you give it a higher charging voltage, it will charge faster, but then it will deteriorate faster as well, right? So there are other key performance matrices as well given in the slide. It's fairly self-explanatory, and the instructor has given it over there, so that's why I have not modeled it. So what the center point of discussion for why storage is, because we want to talk about how microgrids are coming into play. So you now know, right? Because storages are DC, your solar PV output is also DC if it's not connected to an inverter. Then you have, you know, your data centers, they are DC. So all of this load you want to empower in such a way, but you have to convert it into AC, because you have to convert it into various different stages, right? AC to DC and DC to AC to be able to model them. So because this, what it happens, it increases the overall cost of the system and it increases losses as well, right? So this is what it talks about here. So if you have DC, you will remove all of these conversion stages from AC to DC and DC to AC, and you will be able to increase the overall system efficiency. Because there is no concept of this reactive power, harmonics, or frequency, etc. in DC, you don't have to have any problems related to that. So reactive power, what it does is it decreases or increases voltage at a particular node based on how the if it is injecting or absorbing, right? So all of these problems you won't face in your DC system. Also, you won't face is that your the proximity effect and skin effect. So both of them will also not be in picture anymore. So you see your losses have decreased, and you will also face no synchronization issues. So since there is no frequency, you don't have to check and match the zero crossing so that you can have equal synchronization across all the, you know, stages. But so if you have a complete DC system, you won't require any synchronization, right? And since eddy current, hysteresis loss, and skin effect is absent, your losses reduce. And it is because there is no reactances, the impedance of the line decreases, because there is only resistive component present in the line that is faced by the DC, right? And because of that, it is able to transmit more amount of power for a same voltage line, right? And hence congestion of the transmission line can be reduced. That is why you see HVDC systems, right? They are being used because A, you can inject power at any node. B, the the number of losses it experiences is less. So so there are different so let's shift our focus to a DC microgrid. So now we know what is the importance of a DC system, right? Now let's translate it to how DC microgrids look actually. Yeah, someone is speaking. Yeah, Renessa, can you mute yourself? Yeah, thank you. Okay, where was I? Yeah. Yeah, so what you want to now see is how for a fully DC system, how can you have a perfect single DC microgrid, right? Because it makes sense. Your loads can be DC, you don't need conversion stages, no synchronization issues, nothing, right? So DC microgrids are typically of three categories. One is a single bus topology. So in a single bus topology, there is only a single DC bus, as you see here, and all of your loads and and all of your loads and your distributed generation are connected directly across it. So you see your data centers, your communication towers, your heating equipment or your lighting loads all can be directly connected across your DC bus, and you can have all forms of DC uh, powering equipments like supercapacitor, battery, wind, fuel cell, and photovoltaic. So photovoltaic, fuel cell, and wind we have discussed in week 2 and week 3. Week 1 and week 2. Battery as well. What is a supercapacitor? So a supercapacitor is a high power, low energy density device. So it's used to, when I say high power, low energy density, it means that it can have a very high megawatt rating, but its energy capacity per unit volume is very less. So it can be used to power your surges. So let's say when you switch on loads, right, there are surges that are present inside the system. A surge comes, so to power that surge, ultra capacitors are used because they are high power, they have high power density. Then you can have multi-bus topologies as well. So I have not shown it over here, but in a multi-bus topologies, you can have, instead of a single bus, one more bus in which you can have different loads and generation connected, right? And you can have a ring main topology as well. So just like your ring topology in distribution network, this is the same thing, that they are connected across a circular network, right? A mesh network. So you see all of this is DC. This is AC to DC, DC to DC, DC to DC, and this is also DC to DC. And your loads are also connected directly across to this DC bus. So that means that they are also DC in nature, right? So this is how there are three different topologies. So this is also called reconfigurable topology. I'll tell you why. So based on your sections between different sections, you can modify it to convert it into a different topology as well. So this is one architecture. So what do you think in both of them? So I have not shown multibus, but in both of them, what do you think will have a higher reliability? So can anyone tell me, in between both of them, which one will have a higher reliability? So always, you know, what I've done is I've always talked about redundancy. That when I say redundancy, it means that if there can be more than one way to achieve a specific thing, right? That is what redundancy means. That there are more than one systems present. There are more than one relays present. When I say redundancy in protection, in this as well, there is a redundancy. Let's talk about a single bus. If there is some fault in this line, right? So let me draw it. All of these loads across this line, right? This faulty section, it will now be converted into a separate microgrid, right? Because they will be disconnected. This single DC bus will no longer be just a single DC bus. It will be dissociated into into different into two buses, right? And these wind supercapacitor and battery can no longer be able to power the load that is connected to the different microgrid, right? But here, if I remove one section, if fault happens, there is still a separate there is another direction in which a power can flow, so that all of this can be a part of a single topology as well, right? Single bus topology. So what it happens is, essentially, if a section is removed, it converts itself into a single bus topology. So the ring topology has a higher reliability. So always remember this. Right. Modeling of PV we have discussed in a very detailed manner in week 2. So what are the challenges? So, all of this system, when the war of currents happened between Tesla and Edison, we pivoted everything to AC. So we used to have DC loads over there when the electric vehicles over that time were DC in nature. The vehicles were in DC in nature. There was no concept of IC in, internal combustion engine. There was not, they were not in picture. So there were lights were also DC and everything was DC. Then Tesla came with an idea of AC system, right? The three-phase voltages and currents, right? And after that, all of our standards are, set in such a way that they support AC systems only. Not right now. I mean, the picture is much better than it was 7 years before or 5 years before, but still, we still have a we have lack of standards in nature. Then there are protection issues because most of our circuit breakers they rely on zero crossing method, right? Because they want to so they turn off uh, at that instant when the current reaches the zero crossing, right? But because there is no concept of zero crossing in in DC systems, the circuit breaker cannot be designed efficiently. So there is no DC circuit breaker present. What you have is fuses. Then you have sir has shown in his slides different kinds of um, these uh, what where was I? The breakers used, right? So the DC circuit breaker is not used. What they have is they convert it into an equivalent form so that it can be converted. So there are there, but a purely DC circuit breaker is not present. Then DC infrastructure. We don't have DC infrastructure. HVDC is growing. We have power electronics has now, it has strengthened enough to come up with HVAC facts, sorry, HVDC and facts, right? Earlier there was no power electronics. Only after power electronics we have started thinking about, okay, DC is something that we can utilize. Then there is a concept of circulating current in DC. So because in microgrids, if the voltage at two nodes is not same, if the voltages at two nodes is not same, you will have the problem of circulating currents, because then if the voltages are different, there will be different currents in different feeders. So we'll discuss more on this in next week when we discuss DC microgrid in depth. Then we won't be able to feed AC loads until and unless we use converters, and we have high power losses because at DC in distribution networks, R by X ratio increases, right? So resistance is more. Since resistance is more, your power losses will be more in low voltage DC distribution networks, right? So these are some challenges that DC microgrids face. Coming to AC microgrids, so we know all about AC microgrids, right? What are AC microgrids? Which have AC generation and AC loads, right? Everything that we use are AC, right? So this is one depiction of AC microgrid. You can see that the the grid is directly connected across a bus in which we have DC to AC conversions. Right, so this is an AC microgrid in which the bus has AC connections. Right now, but these AC microgrids, they also have, what they have is, we've talked about previously in, I guess, week 4, where we talked about islanding and grid connected mode of operation, right? In that, we talked about how islanding and grid connected modes, because utility is now in picture, right? And utilities directly can be directly connected across the bus because both are AC in nature. They pose certain hazardous situation, like for example they can if the isolated mode is not directly is derived correctly, you will not be able to tell, okay, if your bus is connected, if you are connected across the utility or not, right? So there are some issues with AC microgrids as well. So for that, so they can work in both grid connected and islanding mode of operation. So islanding is necessary, right? We talked about in previous class as well. Let's say that let's talk about hospital. Hospitals are indirectly, they have a huge load and they have uh, the distributed generators as well, like sorry, distributed generations as well, like for example DG sets, they can have solar PV, etc., etc., right? So they are in a sense an AC microgrid. Now in AC microgrid, what happens usually is that they can, if let's say something is happening at the utility side and utility side is not no more in picture, right? So in itself, it should be able to energize the load. The microgrid should be able to energize the load with all the generation it has. This mode is called islanded mode of operation, and because hospital is a critical load, right? You can't have hospital in complete blackout. So for that, you need to have this islanding mode of operation over there. Now for this islanding mode of operation, you need to control your IBDRs in such a way that, sorry, your DGs in such a, so these DGs need to be controlled in such a way that you will be able to, for a grid connected mode and islanding mode, both of the working should be different. And your DGs should have that control inherently in themselves, right? Now, in synchronous generators, what you have is you can control the power inlet in such a way to turbine to cause an effect to power output, right? You can control your synchronous based generators in such a way that you can directly influence the output of the power, and if you are influencing the output of the power, your frequency can be, you know affected. Let's say for this is how it happens. Let's say for this is frequency and this is P, right? So synchronous based generators usually have this droop control, in which let's say for a particular F naught, it's operating at P naught, and let's say some disturbance happened, right? So some disturbance happened and some loss of load occurred, and you have now switched to, yeah, some loss of load happened and your frequency has now increased. So your load decreased and your frequency has now increased. So now this frequency F1 is greater than your nominal frequency F0, right? And now you what you want to do is you want to make sure that this droop or this power characteristic can be modulated in such a way that it can in effect uh, come back to the um, originally how it was behaving, right? So what you do is you change the setting so that for the same power at which it is now working, it comes back to the nominal frequency. So you can shift the characteristic by using what is called an AGC, an automatic governor control. Because you have this capacity, this control over the power, you can control the output and frequency as well, right? So we'll discuss more in the next classes, but I just wanted to give you an idea of how synchronous based generators can be controlled. Then for IBDRs, because you have power electronic converters, right? You use converters over there, and basically what you have is you have two back-to-back voltage source converters. So back-to-back voltage source converters, right? So what you can do is, what they do is in grid connected and in grid and in islanding mode, these converters behave differently. So when I say they behave differently, it's like they have three main operation. So one is grid feeding or following mode. So in this, what they do is based on how the because you have to synchronize your inverter's output in such a way that it does not influence the volt. It is in synchronization it is in synchronization with the voltage and frequency at the power of point of common coupling with the utility grid, right? So what you want to do is you want to synchronize this voltage and frequency, right? So in grid feeding or following mode, your converter or your IBDR Your converter operates the IBDR as a current source. When I say current source, what it does, it injects power based on the voltage and frequency of the grid, right? So your inverters, they have these settings of P star and Q star, reference active power and reactive power. Based on this reference active and reactive power, they can be used to synchronize to the grid's voltage and frequency. So the in a grid feeding or following mode, your converter, what they behave is they behave like a they behave in synchronization or in tandem with the grid. But their only drawback is that they cannot operate in islanding mode, because in islanding mode, you need to have these references P star and Q star coming from the grid, right? Because you want to synchronize it to some voltage and frequency. If there is no P star, Q star, some no reference coming, how can you synchronize them, right? So they cannot operate in in islanding mode until and unless one other type of something else is present. I'll discuss in a bit, right? So what they are called, so the other mode is grid forming mode of operation. In grid forming mode, what they do essentially is they behave like a grid. As the name suggests, they are forming a grid. Let's say the utility grids is out of picture, you want to have some voltage reference for your other loads and converters, right? So you can make your IBDR behave in such a way that they can become a grid forming converter. So IBDR behave as reference of V and F, right? So essentially what they do is they behave like a voltage source. Why should I say they behave like a voltage source? Because a voltage source converter has a same voltage across its node. Come what may the current that it is taking, the voltage will not change. So I hope all of you know what current source and voltage source are, right? Because it's an advanced course, I'll take some things as as I'll assume some things because it's an advanced course. But if you have issues, if you don't know about something, just let me know. I'll be happy to answer. Right. So they can the only so the positive is that they can operate in islanding mode. And one good thing about them is that if they are present and if they behave like a grid, you can have grid feeding or falling mode also work uh, if the microgrid is islanded, right? Because there are grid forming converters which can act as a reference of voltage and frequency, right? Then you have a third stage which is called as grid supporting mode. So in grid supporting mode, as the name suggests, they can shift between grid following mode. Sorry, yeah. So they can shift between grid following mode and grid forming mode. So in both of them, they can shift between so that they can help the grid in stabilization. Okay. So if let's say something happened and your grid forming converter, which was meant to be the primary grid forming is not working, so your grid supporting converters can work. Right. Let me give you some examples. So PV systems are generally configured as a grid following. Um, they are generally done, and batteries, if they are in grid connected mode, they behave as grid following. Right. Then in your grid forming mode, you can have your standby UPSs. Like for example, you have with your they can act as a reference of voltage and frequency so that you can have some so that all other converters can work or all other DRs can work, right? So these are some strategies or in which both of them work. So in grid connected, as I said, only grid following and grid supporting work, and in islanding we have grid forming, grid feeding, and grid supporting work. So there are some ancillary services that these microgrids can provide, right? So as I told you, since they are inverter based resources, we can provide frequency and voltage support. We'll talk about this in next week. Just bear with me. I mean, this will be studied extensively. The PF droop control, then QV droop control, everything will be studied in depth in the next class. But I'm just giving you what is happening in normal operation. What are the ancillary services they can provide? So in normal operation, they can provide frequency and voltage support because they can be used to change the reference in such a way that they can provide frequency and uh, voltage support in your microgrid, right? Now they can reduce losses. Let's say that you are at a very far off place, at a very remote place where there is a huge transmission line connected. So as the transmission line increases, the losses will also increase, right? So if you have a microgrid in place, you can empower that micro some load in that microgrid so that you are not extracting that much amount of power from your main grid, and the losses will be less in that case. Third, you can manage congestion just like that. So I have told you, I've talked about this extensively. So let's say that there is this grid and there is this load and there is this DER, and I say this supports 50 megawatt and this can support 20 megawatt and this line can support 50 megawatt, right? I shouldn't say 50 megawatt, it can support anything. But since the line has a limit of 50 megawatt and the load was 50 megawatt, only the grid was supplying this power, right? The grid was supplying 50 megawatt. Let's say now the load increases by 60 megawatt. Since your line is now congested because it is at its maximum capacity, right? So what you can do is you can use this DR to empower this load and give extra 10 megawatt to it. So in this way, you can have congestion management too. In islanding mode, what you can do is you can use them for black start. I've told you in today as well what black start is, and you can use them for black start capabilities too. And in islanding mode, what they can do is they can act as grid forming for other microgrids. So an isolated microgrid can act like a grid forming microgrid for other microgrids as well. Right, so these are some things that the instructor has discussed. We'll discuss about all of this ancillary services in the next class, so bear with me. And what we discussed today was adaptive protection, and then we moved on to microgrids, DC microgrids and AC microgrids. In adaptive, we discussed why why do we want adaptive protection, because of all the things that we studied last time, right? We have false strips, we don't know the direction, we have dynamics of the in the level of fault current, everything coming at once, right? So if you can make the protection scheme adaptive in nature, you can have a better protection of your system. So we discussed everything: your directional overcurrent relays, your overcurrent relays, plug multiplier setting, time setting multiplier, multiplier setting, time dial setting. Here I got a bit confused, but yes, you are taking the direction of delta IF1 with respect to I1 pre, right? Based on that, you check if it is lagging or leading. So I1 pre leads phi f1, but sorry, so I1 pre is leading delta IF1, but delta IF1 is lagging I1 pre, right? So that means this phi f1 when it is downstream will be negative. So that means it, because it is lagging. So since it's negative, that means the fault is in reverse direction. That is confirmed in this. So you can, I have discussed this in depth today. You can go, and I got a bit confused, it happens. So anyways, then we talked about the importance of storage, DC and battery. If we did a refresher of what we discussed in week 2 and week 3, and then we moved on to DC microgrids and AC microgrids. So any doubts today, any doubts till this point before we continue to our questions? Anyone with doubts? So if there are no doubts, I want someone to at least say no. Okay, so I guess you're shy people, so you won't say no. Okay. So I'm assuming you don't have doubts. If you have doubts, feel free to, write below the comment section. Uh, I will be happy to explain. Yeah. So let's move on to the question. So I told you, right? So the first question is, if the fault current seen by the relay is due to the contribution of only IBDRs, then delta IF is expressed as. So I told you IBDRs and SBDRs, they both contribute differently to, sorry, IF IBDR. So it's 2 times the rated current, and IF from SBDR is 5 times, right? So to be able to map this magnitude appropriately, right? Because we are doing vector addition and we want to map this magnitude appropriately, what we do is we create an impact factor, and in this impact factor we increase this current and decrease the contribution from SBDR so that both of them are at equal footing. So which one of this will be used? I've told you in today's class as well. So what we do is we increase per unit for IBDR and we decrease per unit for our SBDR. And so the correct answer to this would be, yeah, it would be C, right? So what you want to do is you want to have all the contribution of both IBDR and SBDR at equal footing by yeah, by creating an impact factor so that both of them have the similar impact factor. And how do you do this? By using these conditions. So this is for IBDR and this is for SBDR. Right, what is the lower and upper limits for the TDS? So TDS is time dial setting. So a TDS has the limit of 0. It can't have 0, right? Why would you have 0 uh, time delay between your experience when you experience the fault current to the tripping of the relay, right? You have some minimum amount of time, but up until 1 second only. So it's between 0.05 and 1. Why is that? It's because if you decrease, the time taken to trip will decrease, and if you increase, the time taken to trip would increase. So this sits perfectly with what you want to do, right? You want to operate the relay in such a way that you experience the fall for a minimum amount of time before you trip it. So that's where this TDS setting comes into play, and it's between 0.05 and 1. It can never be 0 because you need at least some, otherwise there are surges, right? You can have transients in your system in which current can increase many folds. So you don't want your relay to be tripping at every transient. So for that you have some time delay. Next, what is the polarizing quantity in the superimposed positive sequence method of fault direction detection? So we discussed, right? What is the polarizing quantity? Can anyone tell me? In the superimposed positive sequence method, the first method we discussed. So the delta phi f1 angle that we were measuring it across which polarizing quantity? Okay, so I need someone to say yes or no, right? Yeah, yeah. How would I know? So was it pre-fault voltage? No. Was it pre-fault current? Yes. So you were measuring how your system was changing or how the fault current was changing with respect to the pre-fault conditions. Second, a relay's flux setting can be altered by changing what? So I told you today as well. So your relay, okay, so yeah. So I told you today that a relay is connected across a CT, right? So what your CT does is it decreases the magnitude of the current so that it is within the standard of the measuring of your relay. A relay measures 1 ampere or 5 ampere, right? So it changes it to between these two values. And now to be able to change this plug setting, what you can do is you can change the number of ampere turns connected across connected to your CT, so that once you change the number of ampere turns, you are essentially doing what? You are essentially changing the amount of current it is experiencing, right? This is a transformer. So what happens when you change the ampere turns of your transformer? So what's it? It's I1, A, I2, right? So if you change A, your I1, sorry, I should write it like this. Your I2 is AI1. So if you change A, you're in effect changing the current you're experiencing at the secondary side. So the correct answer is number of ampere turns. The next, capacity of battery is measured in. So this is very easy. I want someone to answer. Don't be shy. I mean, this is a very easy question, right? What is the capacity of a battery measured in? This was discussed today. So it's ampere hours. When the manufacturer specifies the battery's capacity, it specifies in terms of the ampere current that it holds, right? Why is that? Because the energy is a derived quantity and it is nothing but Ah times voltage by 1000, right? So based on the voltage, if the voltage changes, the energy that it stores will also change, right? So to be able to make sure that you have one reference across which you don't have to measure the voltage at all times, it's ampere hours which measures. So you see your battery for the mobile phone, it is generally given in 2600 milliamp hour or 3000 milliamp hour. It's because that tells you how much ampere of current will it hold or will it discharge when it's doing. Next, in which mode of operation the fault current in the microgrid is high? So is it high in islanding mode or grid connected mode? Someone has to answer. Come on. One question someone has to answer. Even if it can be wrong. I mean, I'm not here to, scold you. Anyone? So when it is connected to a grid, let's say there is this fault, right? And there is this DR, there is this grid. You have an I grid fault component coming with the IDR fault current, right? But if this is open, if the circuit is opened, you won't have this you won't have this IGF coming. There will be only IDER. So the magnitude of fault current is more when it is connected to the grid, because grid also supplies a part of that fault current. So due to the bidirectional fault, which types of traditional relays are unable to provide safety protection? So I haven't talked about this, but distance relay, what they do is they measure distance between relay and fault location. So they measure what is the distance between the relay and the fault, and how do they work is they work on the principle that the impedance of the line increases with the length of the line, right? So the working principle is nothing but is directly proportional to length of transmission line, right? So distance relay, what they do is they measure distance, right? But they are alone not so why are they not applicable is because you have a higher impedance at distribution networks, right? So you have to model them at each time. So these can only be used for transmission line, because at that time the voltage is constant, the amount of power they're carrying is constant, and the impedance that it experiences also stays the same. So these cannot be used. So we have already told unidirectional overcurrent relay can also not be used, and instant overcurrent relay in itself can also not be used, right? So the correct answer is all of the above. None of them can be used to, uh, to to use for faults that are bidirectional in nature. Next, when estimating the fault direction using the superimposed currents, the sign of delta phi during the reverse fault when the power flowing is in upstream direction, right? So I told you, if it is in upstream direction, let's do it through the example we already have, right? So when it's in the upstream direction, we know that for upstream, we know F2 is backward and F1 is forward fault, right? So what we do is we check, let's say this delta IF1, and we check with respect to I1P what is the, if it is leading or lagging. So as you can see here in this figure, it is leading, right? Phi F1 is leading I1 pre in clockwise direction, right? So phi F1 is positive. So phi F1 is positive. So when it's positive, what does that mean? It means the fault is forward. And phi F2 is negative because it lags. Now what the question says is that now the question is saying that for a reverse fault, that is at the reverse direction, when the power is flowing in the upstream condition, what is the sign of delta phi? Now I've given you everything. Now you have to tell me what is it. So upstream, reverse, what is the direction of the fault? Sorry, what is the sign of delta phi? It's positive, right? So the correct answer to this question would be positive. You see, every question is based on what you have done in the class today. So you have to answer, I mean. Anyways, I still have to do it. I mean, you can watch it after. Now, in a two-bus system, load is drawing 200 ampere. Let's draw a two-bus system. This is a two-bus system. So it is drawing 200 ampere current from bus 1. So bus 1 is empowering that. Now after fault, the current at bus 1 is increased. Let's say the fault occurred here in this bus, after this bus, somewhere here, right? I can't say this. Some fault occurred here, right? So the fault current now becomes 1500 ampere. Earlier, what was it? 200 ampere. So what is the superimposed current? So I've told you superimposed current is nothing but IF minus I pre, which is 1500 minus 200, which is 1300 ampere. Now the converters used for battery, PV, ultracapacitor and PMSG wind system in a DC microgrid respectively are. So I told you battery can charge and discharge. PV can only give power, right? It cannot be used to charge. Ultracapacitor can also charge and discharge, and PMSG all has to give power back to the system, right? So you need bidirectional for battery, unidirectional for PV, you need bidirectional for ultracapacitor and unidirectional for PMSG. So the correct answer would be A, bidirectional, unidirectional, bidirectional, unidirectional, right? Next, the following type of inverters may not be suitable for the grid connected mode. So grid feeding converters, they are suitable because they require a voltage frequency set point or a reference. Grid forming converters cannot be used because what they do, just a second. Oh, sorry. Yeah. So grid forming, just a second. This was bidirectional, unidirectional, bidirectional, unidirectional. My answer is wrong. Why? 3, 4, 7, 7, 3, 10. Bidirectional, unidirectional. Okay, the answer they've given is wrong. So the answer is bidirectional, unidirectional, and bidirectional, unidirectional. Okay. Next, the following type of inverters. So grid forming in converters, they may not be suitable for the grid connected mode because they will be setting a voltage and frequency reference in themselves, right? So may not be they may not synchronize that good with the grid, so they may not be useful for the grid connected mode of operation. So that is why in this figure, if you have seen, in grid connected mode there is no grid forming strategy. Right. So grid feeding converters are connected to the grid in dash to inject power to an energized utility system. So I've told you grid feeding converters, what they do is they use a voltage and frequency set point, right? And they act as current sources. And a current source act is connected across parallel with high impedance. Why? Because you don't want the amount of current it is uh, yeah, you don't want the amount of current it is giving to change with respect to how much voltage it is experiencing, right? So the correct answer is parallel with high impedance, because they act as current source, and current sources are nothing but they are connected in parallel with high impedance. Next, which of the following battery is suitable for laptops and electric vehicle application? So lead acid were earlier used, but they used to have memory effects, so they are no longer made applicable. Nickel cadmium, they are used for different purposes altogether. So lithium ion can be used because they don't have any memory effect, and they can be used to because they have considerable size, right? There is one more thing, lithium ion polymer. So these are smaller lithium ion batteries which are used in areas where you have size constraints, like for example your mobiles or your smaller notebooks, right? So over there you use lithium ion polymer, but for your EV applications what you use is lithium ion batteries. So the correct answer is lithium ion. So if you're not understanding anything, you can just unmute yourself, we can talk. Next, which of the following operation modes of voltage source converters is suitable during both islanded and grid connected scenarios? So during both, there is only one mode, which is grid supporting mode. In grid supporting mode, you can be in grid connected mode, you can act as grid following, and in islanded mode, you can act as grid forming. Next, which of these is not the microgrid ancillary service during the grid connected mode? So in grid connected mode, it can be used to provide frequency control, it can be used to provide congestion management, and it can be used to provide power quality improvement. But since it's connected across the grid, it cannot be used to do a black start. A black start is always done at that point when you are you want to energize a utility from scratch. So this is all what I wanted to discuss for today. So if there are any questions, let me know. I mean, if you want me to, explain any concept again, just let me know. There are only two people, so I mean, it should be fairly very easy. Anyone with doubts? So no doubts. If there are no doubts, let's end this call. So thank you so much for joining. So I'll meet you all hopefully next week, week 7. It's an interesting week. We'll be where we'll discuss the control of AC microgrids using QV and PF control, and it is a very important topic as well, which you will be using uh, in your studies, advanced studies. So thank you all for joining. Hope to see you all next week. I am ending the call for everyone.